You are in TV now.
On TV.
On TV. Thanks. Well, I would like to thank Professor Borovoi from Universidad de La Serena for giving us this talk. Readers puzzle orbits in real homogeneous space. Please, Professor.
So, gracias a los matemáticos de la Universidad de La Serena por la hospitalidad y por la amable invitación a dar una conferencia en el coloquio. I describe a puzzle for children. We have a pile of stones, a number of stones, and a graph D with n vertices. For example, this graph is called E6. It's his name, it's its name. And at most one stone can be placed on a vertex. So a vertex can have one of two states, stoned or unstoned. We write 1 for a stone and 0 for no stone. For example, we can consider this configuration. These are configurations. Then I want to define moves. Okay. We move as follows. We select a vertex having a vertex I having odd number of stone neighbors. And then we change the state of I. If this vertex was stoned, we make it unstoned. If it was unstoned, we make it stoned. For example, we take this configuration, choose this one, it's here, red. It has odd number of neighbors with one. This is not a neighbor. This is a neighbor. You see, this is not a neighbor. So it has one neighbor with one odd number, and we change it. So we can choose different moves. There is a number of moves possible. We can change this, or change this, or change this. These are moves of the game. Questions? Okay. Now, goal of the game. Given an initial configuration of stones on the graph, we try to reduce the number of stones to make it smaller. And then we ask, what is the minimal number of stones which we get, and how to know it from the initial configuration. It's a children's game. It's a children's combinatorial game. Okay. Now, let's discuss it a little better. I will consider Reader's puzzle. It was introduced by Mark Reader. Look how strange it's written, Reader. In 2005, it was related to some problem from reputation theory. Let G be a simply laced linking diagram with vertices 1 to n. What this means, simply laced? It's a graph with only single edges. Okay, these are all simply laced linking diagrams. Simply laced linking diagrams are these diagrams. This is called AN, it depends on n. This is called DN, again depends on n. It has one branching point. And these are E6, E7, E8. They describe certain symmetric configuration, and they're classified. It is a kind of zoom. So these are simply laced linking diagrams. Okay. We write F2 for the field of two elements. It's just the set of two elements, 0 and 1. And let A1, A2, An be a labeling of D. This means that at every vertex, we write a label, either 0 or 1. It's a term from graph theory. And we can denote by L of D the set of these labelings, and there are 2 to n labelings. We have n vertices, and every vertex we write or 0 or 1.
Stone or no stone?
Stone or not stone, 0 or 1. 0 or 1. Now I again explain what moves are. I already explained again and again. I define move mi, move of the game. How it is in Spanish? Move in a game. How it is in Spanish?
Movida.
Movida. Okay. So we have a move. I define move for any I. So it changes the label from 1 to 0 or from 0 to 1 if the vertex has odd number of neighbors with label 1. And does nothing otherwise if it has even number of labels with the neighbors with label 1.
So if you have 3 ones, you don't do anything to the one in the middle.
Okay, I'll give an example. So we have a certain map from labelings to labelings, and if we have to make it 2 times, we return to the we get identity. I'll show an example. Exactly, you're right, but I'll show an example. So we consider this example. These are our diagram. This is A5. Okay, maybe I put it. This is maybe here. This is A5, A5, and then I don't write the lines, and we choose this one, red. It has odd, but I apply M5. We look at this one on the place 5. It has odd number of neighbors with 1, and we change it to 0. Then we look at what we got, and we apply M2. Now this vertex 2 has even number of neighbors with 1, and so nothing has changed.
It remains 0.
It remains 0. Yeah. Now let's apply M4. We look at this red at 1 at place 4. It has odd number of neighbors with 1. This is odd neighbor with 1. This is 0, so 1. So we change it to 0. Okay, let's apply M4 again. Now it's 0, but as before, the neighbors didn't change. So again, it has 1 neighbor. Odd number of neighbors with 1, and so we change 0 to 1, and we see that I don't need one. No need M for where equals identity, and this is of course for any I M I where equals identity because the neighbors don't change. Okay?
Yes.
Questions? Mm-hmm. No? Okay. Because this should understand, this is very, I can repeat if necessary. No questions? No questions? Okay, good. Okay. Now equivalence classes. I want to explain the game in really what I need. I don't want just to know the minimal number. I want equivalence classes. So, we say that 2 labelings, A and A prime, are equivalent and write like this, A equivalent to A prime, if one can pass from A to A prime by a finite number of moves. So this is an equivalence relation because mi squared is one identity, and the finite set L of D, which has 2 to n elements, decomposes into a finite number of equivalence classes. And we denote this set of classes by classes of D. This is L of D modulo this equivalence relation. And to solve Reader's puzzle means to describe the set of equivalence classes of D, and to describe each equivalence class in L of D. This means that we should, for any 2 labelings, we should know whether they're equivalent or not, and have a family of representative of each class.
And do you know the number of classes?
Of course, first I need number of classes, but not only. I need also to know for every label. I want to every labeling to know whether they are, in which class I should give a representative of each class, and to every labeling say in which class it lives. Questions?
The order is it even always?
What?
the order of the class set.
The order of the
The
class.
order, the number of elements, the
No,
number of classes.
no.
It can be
no,
anything?
no. Wait a little. I computed. I'll compute it.
Okay.
I computed. So example A6. Let's see what's the invariant. How to know when to labels of the same class or not. Here we have this. We start from this labeling. We change, and here I write the same but without zeros. You'll see why it's helpful. I can change to this red 0 to 1, and then I get this. Then I change this red 1 to 0. I get this, and then I change this 1 to 0. I get this. What is the invariant? The number of connected components of bonds. Here we have, here we have. Then okay, maybe again I write. Right? So what we had here, we had 1, 0, 0, 0, 1, 1, 0. I like the line. I write the lines. Okay. This was our labeling. Then I erase zeros and the corresponding edges. And we have two connected components. And this is the invariant. And one can prove it, but it's clear from the example. So if two labelings have the same number of connected, here there were two connected components. And it's easy to show that for this graph, AN, if we have two labelings with the same number of connected components, one, the equivalent. If not, then not. Okay, very simple. Okay, it's a theorem, but it's a very easy theorem. Okay, so proposition, not a theorem, proposition. For AN, we have two labels, A and A prime are equivalent if and only if the number of components of A is equal to the number of components of A prime. Questions? Okay. Example, for A5, we have exactly four classes. This, 0 components, this 1 component, 2 components, and 3 components. We cannot write 4 components, it's clear. Okay, that answers your question for this, for A5, and even for AN. So here's the number of classes. The number of classes is 4, but if we have A7, then the number of classes will be 5. So it can be odd. Okay?
Yes.
Good. Questions? Okay. So now, remember, I should write what is E6, E7, E8. So, because it was, I didn't so right. This is E6. This number is the number of vertices. This is something here. 7, and this. And here, this is 8. And for these diagrams, the number of components is not invariant. Look, here 3 is equivalent to 1. Consider this labeling, it has 3 components. But this red 0 has odd number of neighbors with 1. We can change it by a move to 1. And then we can, now this one, which I show, has odd number of neighbors with 1, we can make it 0. And the same as this is, so we see that this is equivalent to this. So 3 is equivalent to 1.
So you mean the neighbors can be horizontal and also vertical?
Yes, these are not neighbors. These are not neighbors. This and this are not neighbors. You should look at the diagram. this neighbor to this, but not to this.
So neighbors are on lines.
Okay,
vertical
exactly. It's a graph.
Yeah.
The neighbor in
It's
the
just a
sense
graph.
of graph
Yeah,
theory.
yeah, because there you don't show the edges. That's
Of course. The eyes don't show the edges, but you have this picture.
Okay, so I have to look at both.
Exactly. This is why I graph. Exactly. These are exactly. Okay. Now, however, the parity of the number of components is invariant. That's clear because we change 3 to 1 when we merge them. 3 changes to 1, so the parity does not change. You cannot a labeling with even number of components is not equivalent to a labeling with odd number of components. So this is clear. Okay, I continue. Now, however, it is not true that every two labeling with the same parity equivalent. Look at the labeling 0. This is 0. You cannot change it. It's unmovable. It's fixed. It's clear. Now, this labeling, let's call it L3 because it has 3 ones, also fixed. Look, this one has even number of neighbors with 1. It cannot be changed. This 0 also has even number of neighbors with 1. And the same for this is, so it's also fixed. Mi of L3 is L3, and Mi of 0 is 0 for any I. So each of these two labelings is a class, this one set, one point set is a class. One element set is a class.
It's a class by itself.
By itself, so it's not equivalent to any other labeling. And also there are labelings with movable labelings, which you can move, with even and with odd number of components. Okay. Theorem. This theorem I found in the internet. I found a PowerPoint talk, no paper, nothing.
Oh.
This theorem, you can find I looked in Google Scholar for the papers that refer to this paper of Leader who introduced this notion, and I found this. And so the theorem is as follows. If a graph G is a tree, not necessarily Dinkin diagram, a graph, tree containing E6, then there are exactly 2 equivalence classes of movable labelings. Any movable labeling of G is equivalent to a labeling with either 1 or 2 components. There is no proof, some ideas. I wrote to him, he explained the proof, it's correct. Okay. Corollary, for E6 and E8, there are exactly 3 classes, 0 and 2 movable classes, the even and the odd. And for E7, there are exactly 4 classes, 0 and 3, these are 2 fixed classes, and 2 movable classes, the even and the odd. Of course, to prove it, you don't need Ven's theorem, it's just, okay, you can prove it in computer, because it's, or even by hand, because there are not. But if you want to use Ven's theorem, you should show that, for example, for E6, there are no fixed labelings, except 0. You can easily change it up. But okay, it's an easy result. Okay, questions? No? Okay. Because now Dinkin diagrams classify symmetric configurations, very symmetric configurations, which are called root systems. And they in turn classify many different kinds of things, but most important, simple algebraic groups. So, and there are Dinkin diagrams simply laced and not simply laced. And these are non-simply laced Dinkin diagrams. Again, it's a zoo. We have 2 diagrams, B and depend of N, and C and depend of N. Look, they differ by this arrow. That's the same graph, and you should, maybe again I have to write, this arrow are actually inequality sign. So, and this is an equality sign. The vertices are called roots. This is called, okay, maybe I have a bit on the. This is called long, this is long, and this is short. This inequality, this is longer than this. Okay, so, okay, and there are also two diagram, exceptional F4 and G2. And since I want to use it for certain problem, I'll say later about the problem, we generalize the reader's puzzle to non-simply relate to these Dinkin diagrams, and this generalization, okay, and generalization that follows. Okay, when counting neighbors, we do not count the shorter neighbors connected with vertex by a double edge. I'll show you an example. So we take this. So this is long, this is long, this is short. This one is short. So this 0 has one neighbor, this one. Short is not counted. As my student said, long roots don't see the short roots. Okay, so we don't, if 0 does not see short one, so it has one neighbor, we can change it, it becomes 1. Then we look at this one, it has one neighbor, we count it because it's longer.
Longer, yes.
And we change it to this. So this is equivalent to this. Okay. Questions? Okay. I continue. Now, having in mind certain application, I will introduce colored Dinkin diagram. A colored Dinkin diagram is a Dinkin diagram which one vertex is colored in black, while the other ones are white. So, for a colored Dinkin diagram, or excuse me, for a colored Dinkin diagram, we define the moves to the corresponding to white vertices as the above, while for the black vertex, the rule is different. The move mi changes ai if the vertex has even number of neighbors, this one. And if it has odd number of neighbors, then it does not change. So for example, the 0 over this black vertex can mi changes the 0 to 1. And my student didn't like it because he said it's not enough beautiful, it's not nice, different rules, and he wanted to have the same rules. So he changed the graph as follows. Look, for a colored diagram with a black vertex, we call it in white, and formally add a new vertex, which is called boxed one. It has a label 1, and it's unchangeable. We cannot change it. So we have this, and we get now this. And now this does not change the set of labeling. This one is not a part of the labeling. It's formal vertex. And it does not change the rule of the game. So I explained you now why. So here we had 0, and it is changed to 1 because it is black. And here you have 0, it's white, but we can change it to 1 because we have a formal additional vertex. And we cannot change it, we don't have move corresponding to this additional vertex, it cannot be changed. Okay, so it's the same problem, but without black vertices, instead we have a formal vertex, boxed one. That's it. Example, this is dn, and I write also this n because we have this black vertex n, and we make it white and add one additional vertex, formal vertex 1, black box 1. And proposition is that for this diagram, we have exactly 2 equivalent classes. The class of 0, which consists all labeling with odd number of components, and the other class, the class of all labeling with even number of components. Even and odd are not equivalent, and all the other are equivalent. Equivalent. Okay, every 2 labelings with even with even number of components are equivalent, and every two labelings with odd number of components are equivalent. I'll prove it for you. I'll prove it for you. So idea of proof, we take this labeling, then here we have 0, we can push it, and get this. Okay? It's like an angle because here we have 0. Then we took at this 0, we can make it 1 because it has one neighbor with 1. So we inflate it. Then we have this, okay? Then we have this red 0. It has 3, we can merge these 3 components to 1, we have a branching point. So this red 0 has 3 neighbors with 1. So we take it 1, and then we shrink all this as again, and we get this. So 3 is equivalent to 1. Shall I explain it again? Is it clear? I must explain why it's interesting, but now it's up to now it's children's game.
For children.
Of course, for children. He explicado a una enfermera.
Le he explicado a una enfermera.
And similarly, 4 is equivalent to 2. If we had here 4, we take 2 and this 1 and make 1. So 4 in equivalence to 2 and so on. Okay, now I say I have to explain why all this is interesting. And this is a little hard. I have to assume that you know what a group is. Okay. So we need reader's puzzle to compute the real block homology in order to compute the number of orbits of real algebraic groups in their homogeneous spaces. I will explain more. An example. I will not explain all this word. I will give examples instead. Okay. First, we consider algebraic group over the field of complex numbers C. So we read G and C. It's all matrices with determinant non-zero. It's a group, as you probably know. And a linear algebraic group of complex numbers is a subgroup of G and C defined by polynomial equations. Okay. Examples. SLN is matrices with determinant equal to 1. And it's a polynomial equation. Determinant is a polynomial of the matrix element. SON is all matrices in G and C, such the determinant is 1, and G times the transpose matrix is matrix 1. Okay, it's polynomial equation. These are algebraic groups defined over C. Okay. Questions? Okay. Now there is a term of connected and simply connected. You can see topological sense. It's some topological space. You can, or you can just not to look at it. Okay. A connected algebraic group is called simple if it's non-abelian. It has no non-trivial normal of infinite normal subgroups. So the group SLN for n greater or equals 2 and SON are simple. Okay, I will show you. So we can see the group. No, this should be that habit. So you can see that SL2, SL2 has a 2C. And you can see the matrix, matrix 1, 1. Oh. 1, and minus 1, 0, 0. So let's 3. And we have this is a subgroup over the 2. It's central, it's normal, but it's finite. So this group is simple, though it has a normal subgroup. Non-trivial, but it's finite. In this theory, one says that group is simple if it has no non-trivial infinite normal subgroups. So this group is simple. Okay. And SON is simple for n greater than or equal to 5. Okay. Now, the group SLNC is simply connected. Okay, I don't want to explain it. It's some topological term. And the group SONC is not simply connected. It admits a double cover, which is called spin NC, spinor group. There is an exact homomorphism from spin to SOM, this kernel element of 2 elements. This is maybe a definition of the group spin, which if you know, it will remind you. If not, you can live without it. Okay. Now, simply connected simple algebraic groups of C were classified in 19th century by Killing and Elie Cartan. Nowadays, one classifies them using Dynkin diagrams. So we return to Dynkin diagrams. Okay. So Dynkin diagrams are, there are 4 series, which are called classical. They depend on n. It's the same diagrams which I already showed you. It's the same. So these are 4 classicals. This is correspond to SLN plus 1. This corresponds to spin to n plus 1. This is the symplectic group, and this is spin to n. And also, there are exceptional groups which are easier to one says the group corresponding, the simple group corresponding to these diagrams. So this is classification theorem that these are all. It's, as I told you, it's kind of zoom. Okay. Now we can see the real algebraic group. Real algebraic groups can be considered a group defined by polynomials with real coefficients. But I will want to construct it differently. For me, these are okay. SLNR is matrices with determinant 1 over R, but I can consider that complex matrices such as G bar equals G, where the bar is the complex conjugation. These are real matrices with determinant 1. And SUN is a group of unitary matrices with determinant 1. And these are matrices with determinant 1 such as G times G complex conjugate transpose equals 1. So these are 2 groups about which I will speak. Now we consider the real structure rho. It's a certain anti-holomorphic involution. Anti-holomorphic in the sense of complex analysis, and involution means that rho square equals 1. So, and then I say that GR will be elements in G is a complex group, which are stable under rho. So, and I give examples. For SLNR, we just take rho of G equal G bar. Look, here we have SLNR is such G, such G bar equal G. And for SUN, we take the same group SLNC, but rho is different. It is G bar transpose minus 1. And then the formula says exactly that here element of the groups are element in a complex group besides that rho of G equal G. So instead of real group, we consider complex group in this row. It's better, it's easier to work with complex groups and complex varieties and all complex than with real. It's general strategy to solve separately first things of a complex number and then over, say, real numbers.
Because the complex numbers are algebraically closed.
Exactly, because algebraically closed, every polynomial has a exactly. Now definition. A subgroup H, so G is a complex group, and as a group G, H in G is an R subgroup if rho of H equals H. Then we have a real structure on H. We just take restriction of rho to H. Now let H be an R subgroup of G. And we can see that X, G modulo H, is just the quotient set or the vector set, I don't know how you prefer to call it. It's the set of cosets which one learns in the course of group theory. Okay. Now on this coset, on this quotient set, one defines the real structure by representative. Just define GH goes to rho GH. And then we can define X of R as an element in X which are fixed under X. Now, then G of R acts on X of R. But now it can have more than one orbit. But it has finitely many orbits. Finitely many orbits. And a natural question is how many orbits has G of R in X of R? Now I want to explain why it's an interesting question. I give an example. So we consider G and C, then G of R is J and R, H orthogonal group, orthogonal matrices, H of R real orthogonal, and X is the set of all symmetric non-degenerate complex matrices. And X of R is all symmetric real matrices with determinant non-zero. And then G X on X by this formula. We take G, X is a matrix, G is a matrix, and G X on X as follows. X goes to G, X, G transpose. This is the actual quadratic forms, which maybe you learned from the in algebra. And then the question is how many orbits, how many equivalent classes with respect to this action. And the answer is given by Sylvester's law of inertia from linear algebra. And it says that G of R has n plus 1 orbits in X1. There are n plus 1 equivalence classes. Equivalence class it corresponds to the number of negative eigenvalues. This action respects the number of positive and negative eigenvalues, and the equivalence class corresponds to the number of negative eigen. For example, for n equals 3, there are 4 classes, 4 orbits. This matrix, these are representatives. This matrix, 1, 1, 1, which has no negative eigenvalues. This matrix, which has 1 negative eigenvalue. This matrix has 2 negative eigenvalues, and this matrix has 3 negative eigenvalues. This, you understand this notation? Diagonal matrices with these elements on the diagonal. So this is what we know from Sylvester's law of linear algebra. So classification, if you have some classification problem in linear algebra or algebraic geometry or something, and you solve it over complex, you want to classify something over real numbers. First, you classify it over complex numbers, and then you try to classify it over real numbers, and you come to Galois homology. And classification over real numbers is a meaningful problem, as you see from this example. Okay. And of course, one wants to classify, to compute Galois homology for all real algebraic groups, but of course, a group is very bad. For example, simple finite group, you know, it's impossible. So we consider some special kind of group for which I will say something about computation of, calculation of Galois homology. So the answer is given by the first non-abelian Galois homology. We define the set of cocycles by this formula. So we take matrices C and G, there is C times rho of C equals 1. It's such a matrix, it's called a cocycle, and it's denoted by Z. Z1, Z is cycle in German. The first letter of the word cycle. In German, I think it will be maybe 45. I think this is not in German. So the first letter is Z. Okay. Note that 1 is a cocycle. 1 times 1 equals 1. Now, we say that two cocycles are equivalent if there exist A and G, such as C prime equals A minus 1, C rho A. And one checks that it's an equivalent relation, and we call Glock homology, or real Glock homology, is the set of orbits of equivalence classes. Again, equivalence classes. Now, it's not a group if G is non-abelian. Product of two cocycles is not a cocycle. But it has a distinguished element, 1. One is a cocycle, and we look at the class. It's class by itself. Yes? No, it's not. Okay, we take the class of this one. It's called the neutral element, the distinguished element. Now, if we have a subgroup H and G, then okay, I wrote the bad word morphism. Please don't read it. Okay, and then we have an induced map of pointed sets, cohomology of H to cohomology of G. Okay, and we can say what is a kernel. Here we have element 1. It's not groups, it's sets, but we can define kernel. Kernel is preimage of 1. It's a preimage of 1. And there is a theorem of Barat-Serre of year 64 that there is a canonical one-to-one correspondence between the set of orbits of GR in S of R, where X is G mod H, and the kernel of this map. And this theorem is trivial. It's just everything is defined in such a way that it automatically holds. The theorem is trivial, but the definition of cohomology is non-trivial. And it's just defined such that this holds. The theorem is trivial. It just gives the definition, you get it immediately.
The theorem shows that the definition of cohomology is good.
Exactly. The theorem shows that the definition of cohomology is good. Now, we wish to compute all this explicitly so that one can compute the kernel. Okay, it's a finite set. It has a point. So one thinks that it has no structure because you have a set with a point. It has no structure. You think you know the number of elements, that you know all about this set, but it is not, because it has additional structure. If you have two groups, you have a homomorphism, then there is certain map, and this is the structure. So you try to one should try to compute this explicitly in such a way that one can compute the kernel, compute the fibers of the map, or which element goes to which element. Now, and this is almost all what I wanted to say. In the main result of my paper with my student Tsachev and Or of 2016, which is perpendicular to 2014, is that if G is a simply connected, simple R group, real group, then we prove that this cohomology is in one-to-one correspondence to equivalence classes for reader's puzzle corresponding to a suitable coloring of the Dynkin diagram. For example, if G is compact, then the Dynkin diagram is uncolored. If it is non-compact, there are tables from which there is a rule how to find the coloring. So this is the part which I did, and my student solved this reader's puzzle. He did compilation and of all Dynkin diagrams is coloring. He computed the equivalence classes. For some I already told you, and they gave us a kind of table. And we computed this kernel in a few non-trivial cases. Okay. This gives, in particular, the cardinality, how many classes. So for all groups, we know how many classes. But this was appeared a year earlier in the paper by Jeffrey Adams, who did not think on counting, on counting orbits. He just did something, and he was asked, does it has any relation to Glock homology? And he found that yes, and he counted the number, but he did not think about computing the kernel. He counted it using computer for exception group, and he had only the number and not, so he didn't know how to compute the kernel. And we gave an explicit description which permits one to compute the kernel. Okay, and now I give one example of computing the kernel. So we take Dn, I let it just start to show this black vertex, and we take this is Dn, and we throw away one, remove one vertex, this blue one, and we get an minus 1. It's written, okay, it's written. But this is, of course, the same as if I write it like this. It's just an. It's just different way of writing. Okay. And now we write, instead of black vertex, we write this squared 1. It's the same diagram. And now we proposition in for an minus 1 with this block, how to say,
Boxed one.
Boxed one. For this boxed one, there are n divided by 2 ceiling classes. I prove there are no branching points with labeling this one component as the 3 components. Three components cannot be equivalent because there are no branching points. So look at the answer. So we take n equals 9, n divided by 2 is 4.5. Ceiling is the least integer greater or equal to this is 5. And see, these are 5 classes. Not classes, these are representatives of these 5 classes. And they're non-equivalent because we cannot merge 2 or 3 components because there are no branching points. Okay, so we have 5 classes. Okay. Now we define maps maps from labelings of an minus 1 to labelings of Dn as follows. We extend the labeling by 0 to the right. This example. And question, what is the kernel? How many classes for an minus 1 map to the 0 odd class of Dn? And the answer, all the odd classes. All the odd classes are equivalent to 1. Look, n equals, and the number is n divided by 4 ceiling. Example, take n equals 9. 9 divided by 4 is 2.4. Ceiling is 3. These are the 3 classes. And maybe you remember that they all are, that this is equivalent to this. And this is equivalent to this. If you remember, we just push this one to the right and then merge them. So, and this is all which I wanted to say you. So now you may ask me, what is the relation? Why all this why readers paddle is equivalent on built-in diagrams has something to do with Glock homology of real groups, and I cannot explain it here because for this I have to explain what is the relation between built-in diagrams and simple groups, and for this I think I need 5 or 10 hours at least.
5 or 10 hours.
At least.
At
Of
least.
course. So I ask you to believe me that it indeed is related. I explained you what Glock homology. I explained what is reader's paddle on the built-in diagram, and why it is equivalent. I told you, and I cannot explain it because in order to explain, I have to explain the relation between simple algebraic groups and built-in diagrams, and I have no time for this.
Yes.
Muchas gracias.
Ya hicimos todas las preguntas. We asked all the questions. Or
Question, comments?
we interrupted it often.
Do you want to make questions?
No, the first part
As
is
always?
the first part was for children. The latter part not for
No.
children. Rated X The first part was rated G for children, for general audiences.
The
The
first
second part is rated X for adult audience.
So it was very interesting in a way. Don't worry. ¿No hay comentarios? Bueno, agradezcamos primero. Thank you very much.
Thank you for the effort in explaining. Oh, ¿hay tecito o no?
Sí, por favor.
But we are cooking.